Okay, we are moving on to talk about the idea of torque, which is something that you do on a daily basis. For example, when you're trying to open the door here, I'm exerting a torque on the door, and thereby I'm giving an angular acceleration to the door. There is a reason why the handle is as far away from the hinge as possible. The farther away you apply the force, better the effect, easier for you to open the door, right? So we can think of torque as something that can give an angular acceleration to an object. So that's one way to define that. And I can make it clear by saying here that suppose I apply a force at some point on this object. First of all, this is an arbitrarily shaped object that's free to rotate about this axis. So if I exert a force in this direction, like this, at this point, right, at this point P in the object, and the point P is at a certain distance from the axis. So if this is what we call the R vector, position of the point of application of the force, and the force is applied. If I tell you that the force, out of this total force F, if I break it up into two components, you would have a component that's parallel to this, that's F parallel, I'll say, and a component that's perpendicular to this, right? So that's your F perpendicular. If I ask you out of these two forces, which one really makes the object rotate, I'm sure you'll pick the F perpendicular. That's what's going to make this rotate. Imagine that the axis is fixed here, and that force is what's going to make it rotate, whereas the parallel force doesn't really do anything as far as the rotation is concerned, right? So because of that, we write down this torque tau, right? We write the torque tau to be R times the perpendicular component of the force. And if I know the angle between the R vector and the F vector, that's this angle here, F perpendicular is your F sine theta, right? So your torque is the distance R of the point times the force times sine of the angle between them, right? So that begs us to write it as a cross product. So we write the torque as the cross product of the R vector and the force vector, right? So torque is equal to R cross F. So the magnitude of the torque is magnitude of R, magnitude of force, times sine of the angle between them, right? And also, if you think of the direction here, you could either say, well, it's going to make it rotate in the counterclockwise direction. So you can say it's a counterclockwise torque. But a better way is to use the right-hand rule here. You can say that the torque is R cross F. So if you look at your R vector, that's this way, right? And your F vector, I bring the F and put it here. So both the tails are at the same point. And I'm using the right-hand rule, R cross F. So I need to curl my right-hand fingers from R to F. So R to F will give me a torque coming out of the board, coming towards you, right? That means the torque tau is, out of the board. So I'll draw it here. You usually draw it where the axis is. It's coming out of the board as if an arrow is coming out at you. So you represent it with an arrow and a circle. That's the direction of the torque, okay? And the direction of the torque like this means the rotation is like this, okay? So it's a counterclockwise torque, but as a vector, it's a vector that points like this, you see? So that represents the torque from this one, okay? And we'll talk more about this in class. We'll write this as either, the torque tau is RF sine theta. So you can either think of it as R times F perpendicular, but there is another way to think of it. If I extend the line of action of this force, right? If I extend the line of action of this force, since this angle theta, it's the same as this angle theta. And if I drop a perpendicular from the axis to the line of action of the force, right? This is 90 degrees here. This is called the perpendicular distance of the force from the axis. So I'll call it R perpendicular, you see. And r perpendicular is nothing but r sine theta. This is the r, the hypotenuse. This is the opposite side. So r perpendicular is r sine theta. And this is what is called the lever arm, right? So it's called the lever arm. So, so the lever arm for the torque, right? That's r perpendicular, which is r sine theta. So you can also think of the torque as if you combine the r and the sine theta together, that's your lever arm or r perpendicular. So you can also say it's the lever arm times the force, you see. So torque, you can do it, think of it in one of these three ways. You can either say it's just r times f times sine theta, that's basically r cross f, or you can say distance of the point of application from the axis times the perpendicular component of the force, or you can say all of the force multiplied by the lever arm, you see. So we'll spend more time with this. So if you need to apply more torque, you better apply the force perpendicular, so that way all of the force goes into the turning of it, right? Also if you, so it depends on how far away you apply it, how big the force is, and at what angle you apply the torque, right? And just a quick thing about the units. This is meter times newtons, or newton meters. So torque is measured in newton meters, or if this is in feet and this is in pounds, that's the foot pounds, right? So these are the common units that are used. We'll do the rest of the things about torque in class.